Hello everyone, now we are ready to discuss reaction kinetics, a sub-area of chemistry studying how fast a chemical reaction occurs as a function of factors of reaction. We represent the speed of reaction with a rate law, which is a function of a concentration of the reactants mostly and other reaction conditions. We will start from defining the rate law, how to represent the rate law. The first page shows a picture of Usain Bolt. Usain Bolt has made a deep impact in sprint as a world record holder in 100 meters men's race. In Berlin, he set the record of 9.58 seconds for a 100-meter race. Then how fast was Usain per unit time? We are already interested in representing per unit time what is the change. Speed is a term to address the change in distance per unit time, per change in time. So Usain ran 100 meters in 9.58 seconds. So then we can calculate it is 10.4 meters per second. So in unit time, per second, in 1 second, Usain ran 10.4 meters. Likewise, we are interested in how fast a chemical reaction undergoes per unit time, represented by a reaction rate. Now let's move to the definition of a reaction rate. We are humans. We humans are constrained by time. Usually we work 8 hours a day, 5 days a week. So does a chemist. A chemist wants to complete the given task of producing a product within the time frame and thus desires to understand how fast a chemical reaction proceeds. Chemical kinetics now addresses this issue, how fast a chemical reaction occurs, or the rate of a chemical reaction. A chemical reaction has reactants and products, as we have studied so far in previous class, Chem 201. We represent a chemical rate as a ratio of the change in concentration of one of the reactant to a product over a given time. Reactants are decreasing in time, so we add a negative sign. Average rate of consumption of reactant, we add negative sign because this one, change, we representing delta. Delta is Greek letter representing change. Delta in concentration, molar concentration of reactant is now always decreasing. So we put negative there to make the whole rate becoming positive. Average rate of formation of product is now change in concentration of product divided by a given amount of time. Now let's see an example. Calculating the average reaction rate for a gas phase reaction, hydrogen gas and iodine gas. When you put these two different kinds of gases in a reactor and applying the proper reaction condition, temperature and catalyst, the reaction proceeds to form 2 moles of hydrogen iodide gases. Now, in an interval of 10 seconds, we monitor the concentration of hydrogen ion. We find that it decreases as below. So hydrogen iodine and hydrogen iodide. Initially, hydrogen and iodine, they have 1 moles per liter, 1 molar concentration. We didn't have any product initially. Now, after a 10 seconds, for a time duration of 10 seconds, hydrogen and iodine decreased by 0.181 molarity, and hydrogen iodide produced 0.362 because the stoichiometry tells it is 1:1 to 2 ratio. It says 1 mole decreased, 2 moles produced. So 0.181 decreased and 0.362 moles of hydrogen iodide, which is leading up to molarity increase. So finally, 1 minus 0.181 gives 0.819 molarity of hydrogen and iodine. Initially, we didn't have any product. In 10 seconds later, we have now 0.362 molarity of hydrogen iodide present in the reactant. Now let's represent average rate for consumption for each product and reactants. So we are focusing on change. So the rate is now change in the concentration over a given amount of time. So we are focusing on this change, this portion. Average rate for consumption for hydrogen gas is same as for iodine gas because it is now 1-to-1 ratio. They are all same as negative, change in concentration over time. Negative, the change is now negative 0.181 molarity over 10 seconds. So the final is 0.0181 molarity per second. However, average rate for production of hydrogen iodide is 0.362 molarity, increase this much over time period of 10 seconds, which gives 0.0362 molarity per second. I want to draw your attention that the average rate of production is now twice here. So we'll revisit this problem, this example, to find unique rate of reaction rate for this reaction. Now, we are monitoring in order to figure out kinetics. The concentration of reactant or product is monitored over time. Suppose the same gas phase reaction, hydrogen gas and reacting with iodine gas to produce hydrogen iodide. We study this one for a period of 100 seconds in a time term of 10 seconds. Then we can calculate, we measure the hydrogen ion concentration, then we can calculate the difference. 0.819 minus 1, 0.670 minus 819, and that way we can calculate the difference for each time period, and times we are measuring in like time duration of 10 seconds. We can calculate rate for each term. So we can just put this one into a graph, and then we can use this graph to interpret the reaction rate. When hydrogen ion concentration is now translated into a graph as a function of time. So x-axis now time, y-axis now hydrogen ion concentration. Initially, hydrogen ion was 1 molar concentration. Over a time period of 100 seconds, hydrogen ion now continuously decreasing because it is reacting and this one is consumed to produce hydrogen ion. As you see, this one has exponential shape. So hydrogen ion is now exponentially decreasing. We want to see this one, how to represent reaction rate with respect to the hydrogen ion, how to interpret this one in later slides. Now, this slide shows you now rate of consumption of hydrogen ion over time. So initially the rate is high. As time goes on, the rate is decreasing because now less and less. So hydrogen ion is now continuously reacting and consumed. So the concentration of hydrogen ion is decreasing. So then rate should be decreasing because there is less of reactants to make this reaction going. If this one is also, we see that it is exponentially decreasing. Now we revisit this problem. Hydrogen ion and iodine ion making gas phase reaction to form hydrogen iodide per 10 seconds. We found out that reaction of consumption and reaction of rate of consumption, rate of product is different. Rate of production was twice the rate of consumption. Then what is the unique average reaction rate? So in order to find out unique rate, we find out production is now twice of the consumption rate. So then unique average rate. In order to find unique one, we need to divide each one by the coefficient. Here hydrogen 1, iodide in 1, hydrogen iodide 2. So this one is same. But for hydrogen iodide change rate, we need to divide by 2. Then this one divided by 2 gives a single rate, 0.0181 molarity per second. So we can apply this one genetic equation in the next slide. We have a genetic equation, A moles of A, a reactant reacting with B moles of reactant B. As a result, two products are formed, C and D. So C moles of C and D moles of D are produced. Then what is the unique average reaction rate? So average rate is now negative change in A over T, negative change in B over T, and change in C over T, change in D concentration over T. This is the rate. Unique rate is now we have to divide each rate by the coefficient. So 1 over A, 1 over B, 1 over C, 1 over D. When you multiply, they all become equal. So we have only one rate to represent this reaction. We call this one unique rate. Unique rate is now we are dividing each change by the coefficient of the equation. Now what about instantaneous reaction rate? Many times we're interested in instantaneous change. So instantaneous change meaning instantaneous reaction rate means the reaction rate as the time duration between two measurements is now becoming infinitesimally small. So we are measuring one measurement and right after that we measure again. Then the delta, change in delta becoming infinitesimally small, we represent this one very small d. So change delta is just substituted to d here. So 1 over a, dA dt, dB dt, dC dt, dd dt we represent like this way. This one is not instantaneous reaction rate. So our reaction rate usually is represented with instantaneous reaction rate from this point on. Now we define reaction rate. Then which factors are determining this reaction rate? A major factor is now concentration of reactants. As you have a very dense population of the reactants in a given volume of the reactor, then these reactants are constantly moving and they collide. In collision, they make new bonding old bonding is broken, new bond is formed. As a result, products are formed. So concentration is now most important factor, major factor. And there are other factors, nature of the chemical reactants, the reactants orientation, their chemical bonding, single bonding, triple bonding, double bonding, those things. Temperature plays also important part. As the temperature goes up, the particles move more fast with more kinetic energy and they can collide more frequently. The reaction goes faster. Catalysts make the reaction go faster. Surface area also has a role in a heterogeneous system. When you have solid and gas or solid and liquid together, then surface area of the solid is an important factor. Now, when the reaction is slowly moving, effect of diffusion, how fast the reaction moves in a given phase is also a factor. We want to put all this one into a chemical reaction rate. Now, one thing we need to keep in mind is that the rate should be determined experimentally. From a given reaction, we cannot tell the reaction rate. Rate should be proportional to the concentration of each reactant raised to a power, as we discussed in the previous slide. How much each reactant is densely populated in a given reactor, that's now determining the reaction rate. For example, we have nitrogen monoxide and oxygen gas. They are reacting to form nitrogen dioxide with the ratio of 2 to 1 to 2 ratio. Experimentally determined reaction rate is now nitrogen monoxide, the reactant concentration, molar concentration to a square, and oxygen. And K is a proportionality factor. We call this one rate constant. So this rate, as you see here, the rate is not determined by the concentration of reactants. This rate constant K, we'll see later slides, that contains the effect of other factors such as temperature and the effect of a catalyst. We are introducing term of reaction order. The reaction order is now, with respect to nitrogen oxide, it is 2. Reaction order with oxygen is now 1. The overall reaction order is now, we add these 2 and 1 together. This one, third order reaction order 3. And then we'll start from considering the major factor of concentrations of the reactants or products in the following slides. So 2 methods. The initial rate law method and the integrated rate law method will be discussed in the following slides.